Hi, we are discussing the formulation of quantum mechanics. In this session and in the following sessions, we'll be discussing the Stern-Gerlach experiment. Now, the aim of discussing these experiments is to provide a motivation for the mathematical framework. So basically, we are trying to see how the quantum mechanical world behaves in these experiments. Okay, and the aim of the mathematical framework would be to describe this sort of behavior. So the mathematical formalism that we choose has to be suitable to describe these kinds of behavior. Now, we already saw in the double slit experiment that was an idealized experiment, but we saw that electrons obey what's called the principle of superposition, in a sense that electron can be at different places at the same time. And based on this, we suggested that vectors could be suitable candidates to represent quantum mechanical states, to represent electrons. So these things can be seen more clearly from the Stern-Gerlach experiment. Now, a word of caution here, this is not how quantum mechanics actually developed historically. The historical development is more complex. So this is more like a logical development. Okay, quantum mechanics could have developed in this manner, and this will provide some sort of a logical development of quantum mechanics. The main thing that we do in the Stern-Gerlach experiment is to use silver atoms. Okay, we'll basically send silver atoms through inhomogeneous magnetic fields. Okay, and we'll see the deflection. We'll see how these silver atoms are deflected. Okay, so we'll start by discussing the dipole moment of silver atoms, because we know that if the silver atoms have some sort of a dipole moment, they will get deflected in the magnetic field, in the inhomogeneous magnetic field. Okay, so we'll first try to understand the dipole moment of silver atoms, and then we'll describe the experiments and see how these silver atoms will behave in an inhomogeneous magnetic field. And this session will conclude by discussing the phenomenon called quantization of electron spin. The dipole moment of silver atom. The silver atom has 47 electrons surrounding the nucleus. If you look at the electronic configuration, you might have learned how to write the electronic configuration. The electrons are distributed like this among the orbitals. Okay, this S, P, D, F, I think we used to call them as orbitals. Okay, so it's 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, and then we have got a 5s electron. The last electron, one electron, will go to the 5s orbital. Okay, now if you look at all these orbitals, all right, this orbital, the first s orbital, is completely filled. Its capacity is 2 electrons. It has 2 electrons, and this is also completely filled. The p orbital is also completely filled here. Again, this s, p, d orbitals are all completely filled. If you look here, also this s2, p6, d10, these are all completely filled. And we can show that when the orbitals are completely filled, the contribution towards orbital angular momentum will be 0. Okay, so you'll learn how to calculate this when you study what do you say, the angular momentum algebra. So you will have a chapter on angular momentum algebra, and then you will study how to combine this angular momentum, etc. For now, we take it that if the orbitals are filled, completely filled, then the contribution to the orbital angular momentum is 0. Okay, the orbital angular momentum is 0. And if you look at the spin contribution, the electrons with opposite spins pair. All right. So when you put in 2 electrons in the s orbital, the pairing is between opposite spins. All right. So the contribution, since they are all in pairs, since all these electrons, 46 electrons, are in pairs, okay, their total spin angular momentum also is 0. Okay, the total spin angular momentum is also 0. So this means that there is no contribution to angular momentum from the 46 electrons. There is no contribution to the angular momentum from the 46 electrons, from the first 46 electrons, which means that there is no contribution to the magnetic moment from the first 46 electrons. The only contribution to the magnetic moment, or the only contribution towards angular momentum, comes from this single electron, the 5s electron. There is just one electron in the 5s shell. Okay. All right. So there is no contribution to magnetic moment due to the core of the silver atom. So this 46 electron, including the nucleus, we call as the core of the silver atom. The 47th electron also has 0 orbital angular momentum. because this is S shell. S shell corresponds to orbital angular momentum 0. S shell corresponds to orbital angular momentum 0. Okay, so there's no contribution from the fifth S electron, sorry, the 5s electron towards orbital angular momentum. The only angular momentum comes from the spin of this electron, comes from the spin of this electron. Okay, so the only source of any magnetic moment is that due to the intrinsic spin of the 47th electron. The nucleus has a much smaller dipole moment and we'll ignore it, right? It does not cause any difference to our experiment, so we'll ignore the dipole moment due to the nucleus. The 47 electrons are attached to the nucleus, which is 2 into 10 raised to 5 times heavier than the electron. Right? So the nucleus is very heavy when compared to the electron. As a result, the heavy atom as a whole possesses a magnetic moment equal to the spin magnetic moment of the 47th electron. So we say that the entire atom has a magnetic moment. The entire silver atom has a magnetic moment. And where does this magnetic moment come from? It comes from the 5s electron. It comes from just one electron. It comes from just one electron. Okay. So in other words, the magnetic moment of the atom, of the silver atom, is proportional to the electron spin. Okay, this we have already seen in the previous class. So we know that the magnetic moment is proportional to the spin or any angular momentum for that matter. So we can write mu vector is proportional to S vector. And we also saw in the previous class that the constant of proportionality or the proportionality factor that relates the magnetic moment and spin of an electron is E divided by ME. So E divided by mass of the electron. So we'll be taking E less than 0. Okay, so this is a quite accurate proportionality factor. This we have seen in the previous class. So we can write mu vector is equal to E divided by mass of the electron multiplied by S vector. Okay, now since E is less than 0, okay, we already chose E to be less than 0. The charge of the electron is taken as the charge of the electron. It is negative. So mu and S have opposite directions, right? Because this is a negative quantity, we see that mu vector and S vector have opposite directions. Now, if you look only at the Z component, this is a vector equation. Let's look at the Z component alone. So we see that mu Z is equal to E divided by ME SZ. So from here we can say that if SZ is positive, then mu Z is negative because this part here is negative. So if SZ is positive, mu Z is negative, and when SZ is negative, mu Z is positive. Okay. Now I'll make a note here. Some textbooks use the CGS units. So in CGS units, the proportionality factor between mu vector and S vector, it is E divided by MEC. There's an extra C here. Okay, that's because we use the CGS unit systems. In the CGS units, there's an extra C here. You have to keep this in mind. In this case, C is the speed of light. Okay. Also, we discussed the Bohr magneton in the previous class. Now, the Bohr magnitude also we defined in SI units. If you are going to CGS units, it will have a C also in the denominator. Okay. Now, we'll go to a description of the experiment. As I said, we'll be using silver atoms in the experiment. So what do we do with the silver atoms? The silver is vaporized in an oven. So we heat the silver atoms, vaporize it. So this silver atoms will be vaporized. Okay. And with the help of a collimating slit, a narrow beam of silver atoms is sent down to an inhomogeneous magnetic field. So what do we have? We have got vaporized silver atoms on one hand, vaporized silver atoms, and then we have got some sort of an inhomogeneous magnetic field. We'll send these silver atoms through this inhomogeneous magnetic field. Now this is the configuration, the picture that shows the configuration of the experiment. So here you have got the furnace which is used to heat up the silver atoms. So once they are vaporized, they can be sent through these collimating slits. These are basically collimators. Okay, so that we get a narrow beam of silver atoms. Now it is sent through an inhomogeneous magnetic field. So these are the pole pieces of the magnet. Pole pieces of the magnet, and you see that the upper part is sharpened, right? This makes the magnetic field inhomogeneous. So we'll see that the magnetic field is stronger on top and it's weaker below. All right. So in the sense that the magnetic field lines will be crowded on top and it will be more diverged at the bottom. All right. So this is how we produce an inhomogeneous magnetic field. All right. So that's why we write it as an inhomogeneous magnetic field. Now the field is produced by a pair of pole pieces, one of which has a sharp edge to make the field inhomogeneous. Now if you find it difficult to draw it exactly as shown in this picture, you can draw it just like this. Okay, this is a good representation of the experimental arrangement. So since my own drawing skills are rather poor, I have taken this picture from these lecture notes. So you can find it there. Now, this is something that we have seen already. Since the interaction energy of the magnetic moment with the magnetic field is just minus mu dot B, the Z component of the force experienced by the atom is given by, okay, take the negative gradient of this interaction energy and you get, so again, we are talking only about the variation in the z direction. So instead of taking the full gradient, we take simply the partial derivative with respect to z. Okay, so this is the force is given by the partial derivative with respect to z of mu vector dot b vector. And again, we are not worried about the other components of the magnetic field. So you take only the z component, which is the only component that is relevant to our experiment. And this can be written as mu z, partial derivative of bz with respect to z. Okay, now this I have explained in the previous class. I am not going to spend any more time on it. Now we have ignored the components of B vector in directions other than the Z direction. Okay. Now because the atom as a whole is very heavy, right? So we are not sending one electron, we are sending an entire silver atom to the Stern-Gerlach apparatus. So since the atom as a whole is very heavy, we can expect that the classical concept of the trajectory can be applied. Okay, so since it is heavy, all right, it's almost towards a classical limit. So if you're talking about the trajectory of the atom, you can use classical mechanics. Okay, you can use classical mechanics. So in the sense that if the atom gets deflected, so we know that there's a force here. We know that there's a force here. All right. So if you know the force on the atom, all right, and we can use the Newton's equations to find the deflection. Okay, what would be the deflection if such a force is acting on that atom? So you can use the classical equations to find the deflection due to this magnetic force. Okay. Now, with the arrangement given here, so if you look at the expression for force, we had this Fz is equal to mu z and then partial derivative of Bz with respect to z. Okay, this was our expression for the force along the z direction. Now, if mu z is greater than 0, so let's first look at this term. Okay, the partial derivative of Bz with respect to z. Okay, so we said already that the magnetic field is inhomogeneous. It's stronger as we move up the z-axis, right? Because the magnetic field lines are more concentrated towards the positive, towards the higher values of z. Okay, so this means that Bz increases as z increases, right? Bz increases as z increases. So we have got Bz increasing as the value of z increases, which means that the partial derivative of Bz with respect to z is positive. Right? That's positive. This means that if mu z is positive, then Fz is also positive, which means that the Fz is towards the positive z direction. If mu z is negative, the force is also towards the negative z direction. Okay. So in this case, we can call the positive z direction as upward and the negative z direction as downward. Okay, that's what we mean when we say this. When mu z is greater than 0, the atom experiences an upward force, while the mu z less than 0 atom experiences a downward force. So mu z greater than 0 corresponds to Sz less than 0, as we said earlier, and mu z less than 0 corresponds to Sz greater than 0. Okay. Now the beam is then expected to be split according to the values of mu z. So the only thing that can change from atom to atom is the value of mu z. Right? This Bz, the inhomogeneous magnetic field, is the same for all atoms. So the only thing that can change from atom to atom is mu z. So the beam is then expected to be split according to the values of mu z. Right? So if these atoms have different values for mu z, this means that there will be different force acting on each of these atoms, and this will deflect each atom differently. Okay? So in other words, the Stern-Gerlach apparatus measures the z component of mu, or equivalently the z component of S vector up to a proportionality factor. All right. So why do we say that the Stern-Gerlach apparatus measures the z component of mu? Because of this expression. All right. So we can calculate theoretically using classical equations what the deflection would be, and then you can actually compare it with the measured value of deflection. So deflection can actually be measured. All right. The deflection on the screen can actually be measured. Measure the deflection. All right. Then compare it with the classical calculation for the reflection, and from that you can find mu z. Okay, by comparing the classical results with the actually measured value of the reflection, you can find the value of magnetic moment. So the Stern-Gerlach apparatus measures the z component of mu, or equivalently the z component of S vector, because if you know the z component of mu, you also know the z component of the spin. Okay. Now the atoms in the oven are randomly oriented. Okay. These atoms have no preferred orientation. These are randomly oriented. There is no preferred direction for the orientation of mu. So we expect mu to be all over the place. Okay. So if the electron were like a classical spinning object, we would expect all values of mu z to be realized between modulus of mu vector and minus modulus of mu vector. Right. The extreme values. We would expect mu z to go between modulus of mu vector and minus modulus of mu vector, and all possible values between this. These are the extreme values. All right. So the all of the magnetic moment could be in the z direction, and then you would have plus modulus of mu vector. All of the magnetic moment could also be on the minus z direction. Then you will have minus modulus of mu vector. These are the extreme values. But then we'll expect all sorts of values between these extreme values. This is our classical expectation. Right. Now this would lead us to expect a continuous bundle of beams coming out of the SG apparatus as indicated in the figure here. So this is what we expect classically. Okay. Because the orientation of the atoms are all along the place, what we expect is a continuous distribution like this. Okay. Between the extreme values. Instead, what we experimentally observe is more like the situation, right? What we experimentally observe is not a situation like this, but they go exactly to two different locations on the screen, okay? So only two spots are observed corresponding to one up and one down orientation, all right? So you can call it one of them as up orientation and the other one as the down orientation. Right? So instead of getting a continuous distribution on the screen like this, we get a discrete distribution, basically two spots. Every single atom, right? Every single atom either falls here or it falls here. Okay? Every single atom falls here or here, never in between, never in between. Right? In other words, the Stern-Gerlach apparatus splits the original silver beam from the oven into two distinct components, right? Not to all sorts of components, but only two separate components. This phenomenon is referred to in the early literature as space quantization. It's not a good name because there's nothing going on with space here. Right? So earlier we might have studied that this is called space quantization. But in quantum mechanics, so far we have, so in all of physics, we are still treating space as continuous. Right? There's no space quantization actually. It is actually spin quantization. But if you look at the earlier textbooks of quantum mechanics, this particular phenomenon will be referred to as the space quantization. Now, to the extent that mu can be identified within a proportionality factor with the electron spin, only two possible values of the z component of S are observed to be possible. Right? So we said that there are only two deflections. Now these deflections are related to the two possible values of mu. If mu has only two possible, actually if mu z has only two possible values, this also means that Sz has only two possible values that can be experimentally observed. Okay. Only two possible values of the z component of S vector are observed to be possible. Okay. Sz up and Sz down. Okay. So we'll call this as Sz plus and Sz minus. Now, with the magnetic field and its gradient along the z direction, the Stern-Gerlach apparatus measures the component of the spin s vector in the z direction. Okay, since the gradient is along the z direction, what we measure is actually the component of s vector in the z direction. Okay. Now, the deflections calculated using the details of the magnetic field configuration. Right? You can, as I said, you can calculate the deflection. If you know the details of the magnetic field configuration, you can classically calculate this, and then comparing it to the experimentally observed results, we can find that Sz takes values plus or minus h cross by 2, or in other words, you can say Sz by h cross equal to plus or minus half. Okay, so what we do here is that you calculate the deflection theoretically calculated deflection. Okay, theoretically calculate the deflection, and then you compare this. There is an unknown in the theoretically calculated deflection. Now you actually compare this with the experimentally measured deflection. Experimentally measured deflection. Experimentally measured values. Okay. Now, when you compare these two, you see that they are equal. Okay. The theoretically calculated deflection and the experimentally measured deflection are equal if you put Sz is equal to plus or minus h cross divided by 2. Okay. All right. So a particle with such possible values of Sz by h cross are called spin half particle or spin 1/2 particle. All right. The value of h cross are given in different unit systems here. This is in the CGS units. It's 1.0546 multiplied by 10 raised to minus 27 erg second. Okay. In SI units, it's in the units joule second. So the factor here that's multiplied by here 1.0546 into 10 raised to minus 34 joule seconds. If you want in terms of electron volt second, it is 6.5822 into 10 raised to minus 16 electron volt second. Okay. Now, this quantization of the electron spin angular momentum is the first important feature we deduce from the Stern-Gerlach experiment. Okay. So, what do we mean by this quantization of electron spin? It means that when you measure the spin of the electron in a particular direction, you get only two possible values. Okay. You get only two possible values, never in between. The picture here shows what we would expect classically, right? Because if all the magnetic moment was along the positive z direction, then we would get a deflection corresponding to maximum value for this magnetic moment, right? And if it was all in the negative z direction, we would get a deflection corresponding to minus modulus of mu vector. Okay, and the atoms with magnetic moment in between, there's nothing that stops us from thinking that atoms can have magnetic moment between these extreme values. Okay, so they should fall. The atoms with extreme values would fall here and here. All other atoms, okay, would be falling somewhere in between. This is what we expect classically. Right? So the beam should have spread itself over a vertical distance corresponding to the continuous range of orientation of the magnetic moment. So we expect that the magnetic moment can be oriented in all sorts of directions, and if that was the case, we would get a continuous distribution on the screen. Okay. Right. Instead, what we observe is what we have here. Right. There are only two extreme values allowed. There are only two values allowed here, and there are no atoms falling in between. Okay, the beam mysteriously splits itself into two parts, one corresponding to spin up and the other corresponding to spin down. Now, there's nothing really special about the z direction. We just chose the z direction to put the inhomogeneous magnetic field in. You could have put the inhomogeneous magnetic field along the x direction, and then you will see that the beam would split corresponding to two possible values of the x component of spin, Sx plus and Sx minus. All right, you could have put the magnetic field, the inhomogeneous magnetic field, along the y direction, and you will see that the beam would split corresponding to two possible values for the spin along the y direction, Sy plus and Sy minus. And in all these cases, you will see that the values are plus or minus h cross by 2, plus or minus h cross by 2. Sx plus is h cross by 2 and Sx minus is minus h cross by 2. Similarly, Sy plus will be plus h cross by 2, sy minus would be minus h cross divided by 2. Okay, so this can be done. Okay, so what we have seen in this class is that we basically send atoms, silver atoms, into an inhomogeneous magnetic field. All right, and we see that depending on the magnetic moment, we expect that depending on the magnetic moment, the atoms would go to different places. Okay, but what we actually experimentally observed was that it splits into two beams. It splits into two beams corresponding to two possible values for the component of spin along the direction of the magnetic field. Okay, so we are talking about the component of spin, the projection of spin, if you like, projection of spin vector, the component of spin along the direction of magnetic field. Okay, this component has only two possible values, either plus h cross divided by 2 or minus h cross divided by 2. Okay, this is what we call as the spin quantization. Spin quantization. We are saying we are actually witnessing quantum mechanics here, and spin itself is something special to quantum mechanics, and we see that it is quantized. It is quantized in the sense that it cannot take, if you measure the value of spin along any direction, it cannot take any possible value. It can only take one of the two possible values. Okay, so the first important result that we are discussing with respect to the Stern-Gerlach experiment is the quantization of spin. Okay,